Hi, everyone, and welcome to today's live session, Pressure Sewer and Vacuum Sewer Systems, a comparison of risks. I'm Rachel Seiler, today's host and Marketing Communications Manager for E1. Before we get started, I do have some housekeeping notes. All attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and our YouTube channel. Upon successful completion of today's webinar and within 48 hours, you'll receive a PDF of the presentation as well as a certificate of attendance. And finally, we'd love to hear from you. We've allotted about 5 minutes of Q&A during today's session, so please open up that Q&A window to make use of that feature. If we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's featured presenter, Derek Lachut, Director of Engineering for E1. We are in for a treat today. Derek has worked with E1 for more than 10 years and has been involved with project management, sales, pre, post-sale support, local manufacturing support, and contract management. Derek was involved in many pressure sewer projects in Australia and New Zealand, including Mornington Peninsula, where 16,000 properties are undergoing a septic to sewer conversion. He holds a bachelor degree in mechanical engineering from Case Western Reserve University and a master's degree in engineering management from Clarkson University. Besides E1, Derek has held various engineering and operations management roles in aerospace manufacturing companies within E1's parent company, Precision Cast Parts Corp. Derek, take it away.
Hey, thank you, Rachel. What an introduction. And thank you, everyone, for being with us today from around the world. I should say good morning, good afternoon, and good evening. We have a global audience. So as Rachel said, I'm Derek Lachut, Director of Engineering at Environment One Corporation. And today we're going to be taking a look at pressure sewer systems and vacuum sewer systems with a specific focus on looking at different risks. So let's get going. So today's session is going to be broken into two main portions. First, we're going to look at the background of pressure sewer and vacuum sewer systems. I'll attempt to provide some brief description of each system and principles of operation. We'll look at some common applications and major system components. Once we're all experts on the systems, we'll shift our focus and look at risk. I've segmented our risk discussion into three main elements: risks associated with system design, those associated with the construction of the system, and finally, long-term operations and maintenance. So let's get after it. So let's look at the pressure sewer system. So pressure sewer systems are wastewater collection and conveyance systems. In these systems, wastewater flows from the home or business into a unit called a grinder pump station. Inside the grinder pump station, a purpose-built grinder pump automatically activates based on water level. The grinder pump macerates the wastewater into a slurry and discharges the slurry into the pressurized pipe network. Because the wastewater is macerated, the pipe can be a small diameter, starting at 1.25 inches or 40 millimeters. Also, since the wastewater is pressurized, the pipe does not have to slope downward. In fact, pressure sewer systems are installed in flat areas or even uphill, with the force of the grinder pump creating the flow. Ultimately, the system discharges into an existing municipal collection system, or as shown in this image, all the way to a wastewater treatment plant. So there's our pressure sewer system. Now, I need a little bit of help from you. So help me understand what your experience is with pressure sewer systems. Until a few minutes ago, did you even know about them? Have you used them? Is this all new to you? So Rach, let's have our first poll question pop up. We'll give folks a few seconds to submit their answers. How are we doing?
We've got almost 80% participation, which is great to see. So I'm going to close out the poll right now.
All right, let's see how at least 80% of us did. All right, well, look, it looks like a lot of our audience today are familiar with pressure sewer systems. A lot have used as well. And, you know, for those of you that this is new to you, hopefully you'll learn more as we walk through the rest of the session today. So let's keep going. And here we go. So let's talk about vacuum sewers. So vacuum sewers are, again, a collection and conveyance system. Wastewater flows to a property or a group of properties into a vacuum valve chamber. Now, on the other side of the vacuum valve chamber is a pipe network that has been evacuated of air and essentially has a negative pressure relative to atmospheric pressure. That negative pressure is created and maintained by a vacuum pump station. I'm trying to circle right there. Back to the valve chamber, when enough water has entered that chamber, a vacuum interface valve opens and allows a set amount of water followed by a set amount of atmospheric pressure air into the chamber. That differential air pressure, that atmospheric versus the negative pressure in the pipeline, essentially pushes that amount of wastewater into the pipe network. Now, the pipe network is comprised of a series of lifts, and between those lifts, the wastewater flows by gravity. After several cycles of the vacuum valve, the wastewater will eventually reach the vacuum pump station where there's a collection tank, and then traditional sewage pumps will eject that sewage into a force main, pumping to an existing collection system, or again, all the way to a wastewater treatment plant. So kind of just a theory of operation of vacuum sewers. So again, help me understand more about you. Where do you stand? Have you heard of vacuum sewers before? Used them? What are we learning? So let's have that next poll question. All right.
Okay, ready for the results?
I'm on the edge of my seat.
Dun, dun, dun.
All right. So look, again, we have some familiarity with vacuum systems. Not a lot of users out there, but again, some of you have been. So I'm curious to hear from you as we continue to walk through today's presentation, and definitely some new folks out there as well. So again, hope we're all going to learn something. So we'll just keep on moving. And I will say the description of those systems, very, very brief. There's a lot of other materials out there, both from E1, and you can find different materials on YouTube or other resources to help you learn more about those systems. So just a kind of a real quick overview. But let's look at some similarities between pressure and vacuum sewer systems. So first and foremost, they are collection and conveyance systems. These are wastewater collection systems. Now, because they're collection systems, they need to lead somewhere, and they need to discharge into something that is or leads to treatment itself. So there's no treatment that's really occurring within these systems. Both systems can be characterized as utilizing small diameter pipes. And really, when we say small diameter, this is always relative to gravity collection system, kind of the standard, if you will, when a lot of people start to think about wastewater collection systems. Similarly, both systems attempt to reduce, and in some cases eliminate, inflow and infiltration. Again, inflow and infiltration is something that's unfortunately exists in practically every collection system around the world, and plagues certain users. So these systems have some novel ways to address inflow and infiltration. Most of the time, the pipe is going to be shallower than you would find in an equivalent gravity sewer. In the pressure sewer, because we're pumped and we don't need any grade on the pipe, we can stay as shallow as we're allowed to, either by code or the climate allows us, and vacuum systems as well, having those lifts help prevent the pipe from getting too deep. And look, both systems, and in fact, all collection systems do require some level of maintenance, whether it's on the network itself or any of the mechanical items within that system. So again, real brief, kind of high level, not comprehensive list, but some high points. So where there are similarities, of course, there must be some differences. So let's look at our Venn diagram. And when we look at pressure sewers, the first difference compared to a vacuum sewer systems is, pressure sewer systems at no point after that grinder pump do the pressure sewer systems have any reliance on gravity. The grinder pumps themselves create all the, as I call it, the motive force, right? That flow that is pushing that wastewater to its destination. Now, because a pump is involved at each site, electricity is required to operate those grinder pumps. So electricity is required on each site. And the systems can generate pressures up to 185 feet of head, or I should say we design systems up to 185 feet of head, E1 systems. And those of you in metric, that's about 56 meters of total dynamic head. So that's what enables pressure sewer systems to pump long distance in a straight line, or say up and over a big hill. Looking at vacuum systems, sometimes vacuum systems are referred to as vacuum assisted gravity sewers, because in between those lifts, the pipe is laid at a slope or a grade, and we allow gravity to help move that wastewater line along in between those cycles of that vacuum valve. And essentially that differential air pressure is the motive force. Now, creating that differential air pressure is the vacuum pump station. This is really a critical central piece of infrastructure, whereas in the pressure sewer side of things, we don't really have any main infrastructure. The individual grinder pump stations that are located at the individual houses do all the work. There's no central infrastructure. Again, there can be differences at individual sites in an E1 pressure sewer system. Each grinder pump is identical at every location, whereas in a vacuum sewer system, there can be some individual differences that are required, really how a valve is tuned, how much air and how much liquid we allow in every time that valve cycles. There is a limit to the amount of total dynamic head loss that's allowable in a vacuum system. Now, this is also limiting the distance that we can service from a vacuum pump station, but also the elevations that we can face. We're limited by what atmospheric pressure allows. So it's not the matter of putting a bigger vacuum pump in, because atmospheric pressure is our motive force. We're limited by the capabilities of what atmospheric pressure provides for us. So again, not another comprehensive list, but just some highlights. So looking at some applications. So pressure sewers really help us overcome challenges presented by a variety of terrains. And it really just all comes down to cost. And pressure sewers have kind of demonstrated to deliver best value for money in a lot of different applications. You know, as an engineer, I really believe that nothing is impossible, but certain things are really not cost effective, or to put another way, are cost prohibitive. You know, when we look at flat terrain, pressure sewer systems are a great tool to solve sewering challenges in flat areas. With a gravity sewer, because the slope is required, we're going to get very, very deep with that flat terrain. Similarly, when that flat terrain is also wet, we're going to have construction challenges, because not only are we digging deep, but now we've got to contend with water. Rocky areas, from a constructability standpoint, especially, pressure sewers have a lot of value because the pipe diameter is small. And once we talk about construction, we'll talk about construction methodologies, but especially if we can utilize directional drilling, it really simplifies the installation in rocky areas. And as a result, we see a lot of pressure sewers utilized to service rocky communities or areas characterized with a lot of bedrock. And finally, the pressurized nature of the system, the ability to overcome 185 feet of total dynamic head, or 56 meters, allows pressure sewers to service a lot of hilly terrain or undulating terrain. Looking at key applications of vacuum sewers, we see some similarities, but because of the limitation of atmospheric pressure and basically that static lift, vacuum systems are primarily found in areas that are characterized as flat, and also areas that are characterized as wet. And we see a lot of vacuum sewer systems in coastal areas, or areas next to, again, the sea or lakes, rivers, those sorts of things. So applications a little bit more limited when it comes to vacuum sewer systems. Let's look at the components that we'll find in pressure sewer systems and vacuum sewer systems. And again, for those of you that are new to this system, these systems, hopefully this provides a little bit more information on the details. So first thing, with a pressure sewer system, we're going to start with the grinder pump station itself. So I'm kind of circling that entire grinder pump station itself. It has the actual pump itself, that grinder pump, inside of a collection basin. And the configuration, exactly what this looks like, varies based off of product configuration, region, manufacturer, those sorts of things. But what we're seeing here is kind of a standard E1 unit. And the last component that makes up the grinder pump station is an alarm panel or some sort of control system for the unit. Now, downstream of the grinder pump station, the rest of the pressure sewer system is the pipe network. And the pipe network I mentioned earlier, small diameter, starts at 1.25 inches. So the pipe we see here would be 1.25 inches or 40 millimeters. And then as it connects into other grinder pump stations into a common force main or rising main, that pipe will increase in size. A pipe network also incorporates a series of valves for different purposes, whether they're air release valves or isolation valves, different valves that really provide some installation and operation and maintenance flexibility. So those are kind of the two main components of the pressure sewer system. Looking at our vacuum system. So major system components of the vacuum system start with the vacuum interface valve and chamber, kind of what I'm circling there right now. And again, the configuration of this varies by manufacturer, by product configuration, but typically there's a sump and some sort of level control, sensing device, a valve, and some actuation controls inside of that chamber as well. Next is the pipe network. So the pipe network itself has this series of lifts that create this sawtooth profile necessary to ensure the wastewater doesn't fill the entire cross section of the pipe. This ensures that vacuum pump station is able to create negative pressure throughout the entire network. And without these periodic lifts, the wastewater kind of slug or volume of wastewater could actually block the whole cross section of that pipe. So that's why you often see those lifts and other valves that you'll find in that pipe network. And finally, the vacuum pump station itself. And this is a fairly complex piece of central infrastructure. It contains the vacuum pumps themselves, and the quantity of pumps and the type of pumps really depends on the system size and maybe some need for redundancy. Then there is a sewage collection tank and then traditional sewage pump. Again, quantity of pumps, type of pumps, configuration really varies from project to project, manufacturer to manufacturer. Keeping everything organized is a control system driven by computers or PLCs and other SCADA systems. And vacuum pump stations typically also need to be accompanied with some sort of odor control or management system. The exhausting air from that station can be kind of smelly, and to prevent complaints from nearby properties and things like that needs to be treated. Finally, many vacuum pump stations require some sort of emergency power supply or generator. Since there's kind of very little storage in the event of a power outage inside of that system, we need provisions for emergency power. And kind of my image here shows an emergency standby generator located on site. All right, so that's kind of the first half of the presentation done, that system background. Again, if you're new to any of these systems, I encourage you to reach out, look at E1 for resources for pressure sewer systems, look online, look in some textbooks for more information about it. But we're going to talk about risks now. So, as I think about and approach risks, the first thing we have to do is acceptance, right? That's the first step. We have to accept that risks are going to exist in any facet of life, whether we're dealing with a sewage collection and conveyance system or life, risks are unavoidable, and I'm sure you would all agree. But risks are relative, between options or between people. Something that's risky to me may not be risky to you, or vice versa. Next, there are risks that we know about, and there are risks that we don't know about, but maybe we know they might occur. And then there's the dreaded unknown unknowns that are going to be there. So, we can try to imagine all the risks that are going to be there, or that we know are going to happen, and again, need to be prepared for what happens when things don't go as planned, if you will. It should come as no surprise, that people in general, especially engineers, seek to minimize risks as much as possible. And when we do that, what we often do is we develop contingency plans. So yes, we know risks are unavoidable. We know that we can identify the risks, we try to minimize the risks, but at the end of the day, they're still going to be there. So developing some sort of plan B, if you will, or contingency plan is important. When we roll all this together, risks cost money. They can be characterized as money, that whether that's, contingency in a capital budget or an operational budget, or just planning in general. And okay, last but not least, when I think of risk, I think of one of my favorite board games in the world. Risk, of course, is the game of world conquest. Not the point of this presentation, but my strategy to any of those novice risk players are to fortify your position in Australia and then just continue to build armies. But a different webinar, stay tuned for an invite to that one. So remembering our three categories, let's begin looking at risks in design. And let's start with pressure sewers. Now, E1, we attempt to address and minimize the risks in design of pressure sewer by developing a methodology that is flexible, conservative, and as accessible as possible. We don't have a lot of secrets, if you will, about our approach to design. The one secret I will say is that we are conservative, if you didn't already know that. Most pressure sewer systems operate well below that total capacity as well. So just because a pump is capable of operating at 185 feet of TDH doesn't mean we design that pipe network such that that pump is always going to operate there. Speaking of pumps, E1 specifically utilizes progressive cavity style grinder pumps specifically for their resiliency and their ability to mitigate some of the uncertainty and risks, if you will, that occur in design. And two of those are, what happens when the hydraulics are greater than what we had anticipated. Say there's more pumps operating, the flows are greater, the pressure in the pipe network is going to be greater. A progressive cavity pump has what we often refer to as reserve hydraulic capacity. So our design limit of 185 feet isn't the ultimate capability of the pump. The pump is capable for intermittent periods of time to operate above 185 feet to deal with, again, some of those what ifs, some of those unknowns. On the flip side, in the event that flows are less than we anticipated, progressive cavity pumps generate a consistent flow rate and are able to self-scour a pump. In the event that solids begin to build up in a pipe, the cross-section of that pipe is reduced, but the flow rate through it maintains the same. So eventually we'll hit a scouring velocity and will help keep that pipe clean even during those low flow periods. So the progressive cavity pump is key to helping mitigate risks of design with pressure sewers. We have non-critical precision, and this goes back to that conservative approach with it. Yes, we want the inputs into our design process to be as accurate as possible. Sometimes accurate information isn't available or it's not available at the right phase of the project. And in many cases, we are able to produce an acceptable level of detail with our designs with not the greatest or not the most precise information, because we're able to absorb some of those unknown or unplanned changes that will occur. Now, it's not all rosy, I suppose. Each grinder pump station must have access to a power source. So system designers do need to take that into consideration when they're evaluating options. Is there a location where I can find power to power this grinder pump station? And likewise, grinder pump stations are most typically located on private property when we're talking about residential settings. So is there a location, or can the unit be sited on this property? So just some risks in design. Let's look at risks of design of vacuum sewer systems. So, the design methodology of vacuum sewer systems does pose some risks. It's generally more complicated and it relies on a lot more inputs, assumptions, and calculations. And again, I'm a fan of a design spreadsheet too, but when we compare, we're talking about comparative risks. There's a lot more inputs, a lot more precision that's required when we are designing vacuum sewer systems. Sizing of that pipe network is critical. So we do need to be confident about the flow flows that we're going to receive, especially when we're looking at how do we size the network, how do we size the vacuum pumps, how do we tune those vacuum valves. It's really critical that we know as much of that information as possible. And the reality is we don't always have that information available. In general, vacuum sewers have much limited reserve capacity to help for some of those unknown unknowns or unplanned growths that may occur. We can design in additional capacity. We can make pipes larger, we can upsize vacuum pump stations, but we need to do that at the project outset in order to get the best result. Upgrading vacuum sewer systems in the future is definitely possible, and it's done, but it's definitely going to be more costly. And it might be impossible. So understanding that upfront, what's the potential future is absolutely critical and does put a lot more pressure on that system designer. Talked about limited static loss. Our limiting factor there is atmospheric pressure. So again, why you won't find vacuum sewer systems in hilly areas, it's simply, you know, there's some technical obstacles to allowing that to occur. System designer must keep in mind that a vacuum pump station needs to be located. To be most successful, vacuum pump stations are located in a central location to the project, so it can create kind of consistent vacuum pressure radially out from that center location. Also, land needs to be reserved or purchased in order to site that vacuum pump station. So whereas grinder pump stations are located on private property, you know, there's the kind of the comparative risk. Yes, that infrastructure is not located on private property, but the central infrastructure does need to be located somewhere. Speaking of that vacuum pump station, the design is definitely more complex. There's a lot of parameters that need to be considered. And again, the accuracy of getting this information is absolutely critical. And this is why system suppliers offer detailed design services at a cost to other consulting engineers or municipalities, land developers, whoever their client may be, due to that complex nature, some proprietary kind of know-how and that precision that is needed. And last but not least, there is definitely an ideal number of connections required to make vacuum sewer systems feasible. When we start looking at the cost per connection, because especially that vacuum pumping station, you know, it's a large expense. So we need to make sure there's a large enough project to make it all worthwhile. Again, I didn't specifically discuss that with pressure sewer systems, but pressure sewers don't really have that same economy of scale. So we talked about design, let's talk about construction. So pressure sewers do allow for a tremendous amount of flexibility with the methods and methodology of installation. Starting with that pipe network, pressure sewers are often installed using horizontal directional drilling, as well as kind of an open cut trench method. Especially when it comes to installing a collection system in an established community. You know, we often put pressure sewer systems in septic tank replacement projects. The ability to horizontally directional drill the pipe can significantly reduce construction costs and other costs associated with things like remediation. Since no slope is required, it further simplifies the installation. There's no need there's no needed or critical slope of the pressure sewer pipe. Again, you know, if it's flat, if it goes uphill, if it goes downhill, it's really not critical to the operation of the system. Now, if you recall our discussion about risks, we mentioned that there are known and unknown risks. Well, that really comes into play during construction. Even with the best preparation, there will be unknown underground obstructions that will be faced by system installers. So whether it's unmarked utilities or rock strata, vegetation, all this kind of stuff will be encountered. Since we have this real flexible design nature and lack of criticality on the system hydraulics, the contractors can basically be given free range to reroute the pipe network in order to mitigate those underground obstructions. Redesigns really aren't necessary. We can always rerun hydraulics with different elevations if we have to go under an unmarked gas main or something like that. But in most cases, the flexibility of the network just says, you know, go an extra few feet deeper under that gas main and we'll be fine. Now, at some point, the grinder pump station will need to be installed, and whether this is the responsibility of a homeowner or the responsibility of a central entity or contractor, there are always risks when working on private property. So good coordination, transparent communication with the property owner is important for seamless outcomes. And similarly, the power supply for the grinder pump station must be installed, and as mentioned, it's usually connected or tapped from the property owner's supply. And at the end of the day, this on-property installation definitely involves a combination of civil and electrical works. Looking at risks involved in the construction of a vacuum sewer system, first starting with installation method, due to the precision slope needed on that sawtooth pipe, vacuum sewer systems nearly always must be installed with open trenching. There may be some times when directional drilling could be possible, but the majority will be installed with trenching. And this can pose some cost and technical risks. Remember, most vacuum sewer systems are in flat and wet areas, so it's likely that they'll be contending with things like groundwater and running sands and all those sorts of things. And again, when working in an established area, if vacuum sewers are being investigated for that septic to sewer project, open trenching will require the costs associated with restoring roads and driveways and landscaping and all those kind of existing things there. So restoration costs are much higher. In order to create the lifts needed for the vacuum sewer pipe network, the contractor must construct those lifts from a combination of straight pipe sections and directional fittings. The number of fittings in a vacuum sewer pipe network can be really an order of magnitude more than that you'll see in a pressure sewer system. In any system, each fitting is a potential liability and adds cost to that network. Looking back to our construction unknowns and those underground obstructions, an unmarked utility, a granite boulder, something like that will require a system reroute and redesign, or the high cost to move those obstructions. And if you see from this image here, you can see, this vacuum sewer system going in with open trenching, trying to weave between all of those existing services definitely creates some risks and complexities. Since most vacuum sewer infrastructure is installed in the right-of-way or a utility easement, like a gravity sewer, this means that the gravity drainage lateral, that usually 4-inch pipe that flows from your house into either the gravity system, pressure sewer system, or vacuum system, is going to be longer in a vacuum system or a gravity system. Now, all wastewater networks suffer with inflow and infiltration, and most wastewater network operators will tell you that 40 to 50% of it is infiltration they can't control because it comes from this piece of pipe or these private sources. So one thing to keep in mind is a risk of construction. We are actually increasing the length of that gravity drainage versus if we were to have a pressure sewer system, we'd actually decrease the length of that drainage because oftentimes that grinder pump station is located on that private property. Now, vacuum pump station construction is a major undertaking. It's a coordination of civil, structural, mechanical, and electrical work. So a lot is involved there. And when we really roll this all together, vacuum sewer systems do require more skilled and experienced installing contractors. And those definitely do exist, but may not be in the region the project's located or at the budgeted price point, given that skill level needed. So kind of our last little piece here is operational risks. Now, first, grinder pump stations do require electricity. And risk reduction or contingency measures with grinder pump stations are first that there is a collection tank as part of that grinder pump station. And so there's some inherent emergency storage on site within that collection tank itself. During a power outage, oftentimes those high water consuming appliances won't be using, so that storage is even greater because typically we're only talking about like using the toilet and maybe some light washing, especially depending on how you generate hot water. Pressure sewer systems also have provisions for emergency power. So a municipality or a homeowner can connect a portable generator to the unit to operate that system itself. So, but electricity is definitely still needed. Now, reactive maintenance is necessary to grinder pumps. There is no proactive maintenance that's required, or routine maintenance, but at some point in the future, the grinder pump station, the grinder pump specifically, will need to be maintained. But again, this is usually in a reactive manner. Grinder pumps and grinder pump stations are often viewed as household appliances. So think of them much in the same way as you look at your refrigerator, and service life and service interval and maintenance needs of any of those major appliances. Now, end users can be involved to report faults. The most common method is that that alarm unit and that control unit, part of the pressure sewer or the grinder pump station, does have an audible and a visual alarm. So the homeowner, the end user, is involved. They are aware when there's an issue with their grinder pump station and can report that fault. And many system operators, municipalities, water utilities like that model where the homeowner is involved. But those that don't, and those that want a proper kind of flush and forget methodology, there are telemetry options available to notify an operator before an end user is aware of any problems. Now, from an operation standpoint, grinder pump stations are autonomous. And what I mean by that is they kind of operate off their own devices, and the operation of one grinder pump does not really interfere, or that grinder pump doesn't really care what the grinder pump next to it is operating. Likewise, when there's a fault at one site, it doesn't impact the operation at an adjacent site. So they're kind of separate and autonomous, and really the user behaviors are really what drive the reliability of those units. And finally, E1 specifically has gone through a lot of work to make sure that equipment is as serviceable as possible. Now, a lot of municipal wastewater operators understand the concept of pumps and pumped networks, so troubleshooting is a lot more intuitive. Whether it comes to the hydraulics or the pumps themselves. So we see lower skills required for operation of that pressure sewer system. And looking at our operations of vacuum sewer systems. Now, the first thing is, one of many key differences, I suppose, is that in a vacuum sewer system, there's no active grinding or maceration of debris. It's relying on that differential air pressure to force the water and any debris that might be in the water into the network, and relying on that high velocity. Now, in the event that there are some hard debris and some maybe defects in some of the pipe material, it is possible that large debris could enter the vacuum pipe network, and traveling at a high rate of speed could act to damage or cause that network to fail, especially in an element like this at a sharp direction change. Something to keep in mind. There's no active maceration or active grinding of that debris. We're just forcing it all through and hoping for the best. Next, there is the need for higher skilled operators, especially when it comes to the vacuum pumping station. Now, because this is a critical piece of central infrastructure, it needs to be online basically all the time for the system to work. There's constant monitoring, constant preventive maintenance at that vacuum pump station. Likewise, at the vacuum interface valves, most system suppliers do recommend some routine maintenance on those valves themselves, again, to ensure reliable operation of that. And that really kind of plays into the next one. The reason why we need preventive maintenance on those valves is because a fault at one site may disable adjacent sites or the entire network. And, kind of specifically, if a valve gets clogged or hung up or has some sort of issue and hangs open, then that can affect the vacuum, the negative pressure basically in the rest of the network, and start to impact service at adjacent properties or adjacent connections. So kind of the anecdote is a user on one property is flushing a lot of debris, and it's trying to be sucked through that network. And if it hangs up a valve and hangs open, then the properties downstream or upstream that are doing the right thing lose their service because of one person kind of doing the things that they shouldn't be doing. Now, uncontrolled inflow and infiltration can cause some significant impacts to all collection systems, but more so vacuum sewer systems versus some others, because of a precise air water air mix that occurs. So that valve opens and it allows a certain amount, there's based on timing, it allows a certain amount of water and a certain amount of air into the system. Now, when that ratio gets out of whack, say there's too much water in the sump, and there's not enough time for air to enter the system. Now, air, that atmospheric pressure air, is our motive force. Eventually, what happens is the system becomes what is called waterlogged, basically stops operating correctly. In order to reset that system, all that extraneous water, all that inflow in the system needs to be removed, needs to be sucked out of the system so that system can be reset. Kind of the last point there, it can be more challenging to identify where faults occur at a vacuum pump station. In the pressure sewer system, because we have the local alarm system, and because it's just the grinder pumps that are part of the network, that's what's creating our motive force. If there's going to be a problem, it's going to be at a grinder pump station, and that grinder pump station is going to let us know through that alarm system, and whether that's reported by the user or through a telemetry system. In a vacuum sewer system, you may not have that same environment unless there's telemetry installed on the valves. You may not know where they're occurring. I will say, however, that telemetry systems are gaining popularity from system suppliers, and it's almost seen now as a necessity instead of a nice-to-have add-on. I think system suppliers have seen the challenges of operating the system and now almost really require that. I would just say that if you're working on a project and considering a vacuum sewer system, make sure you're considering the costs associated with that telemetry system. So look, this is a little bit shorter of a format than some of our other presentations, but I really want to wrap things up and have some time for some Q&A. But just to summarize, as a reminder, again, risks are everywhere in life, in every collection system, whether it's pressure sewer systems, vacuum sewer systems, or gravity systems. E1, as the originators and the innovators and market leaders of pressure sewer systems, we believe that we've done a fairly robust job of identifying the known risks and some of the unknown risks and creating products or techniques that help manage and mitigate those risks. And look, the vacuum sewer suppliers have done much the same, but because of the criticality and a lot more of the construction unknowns and operational unknowns, there's a lot more unpredictability, and oftentimes that manifests itself into unexpected operational costs or unexpected construction costs. And at the end of the day, my ask to everyone joining us today is just to make sure decisions are based off of real views of risks and looking at track record of a specific product and a specific supplier, looking at those users of that specific product or that specific technology and understanding their actual experiences really helps us make the best decision. And it all kind of boils down to long-term impacts, and that's another way of saying looking at real life cycle cost analyses. But again, look, at the end of the day, E1 believes that pressure sewers have demonstrated a lower risk when it comes to planners and system designers through a lot of those conservative measures that we take and flexibility of pressure sewer systems, the construction of the system through horizontal directional drilling and a lot of those other characteristics, non-criticality, and finally, long-term operations and maintenance of the systems. So that's what I have for us today. And I'd be really pleased to see if we have some questions that we could open the floor and see what we got, Rach.
Okay, Derek, thanks for that excellent presentation. We did have some questions come in. And I think you addressed this, I'm pretty sure you addressed this at the beginning of the presentation, but just in case we had some a latecomer here. Could you provide an example where vacuum sewers are more viable than pressure sewers? What conditions, perhaps?
Yeah, so we see vacuum systems most often in flat and low-lying areas. Again, because the motive force in a vacuum sewer system is atmospheric pressure, differential air pressure. So really, it's the only application for vacuum sewer systems are in these flat and low-lying areas. So a lot of coastal areas will find them. Now, because of the high cost of a vacuum pumping station, usually what we'll see are vacuum sewer systems that are quite large. So I think that's where the vacuum sewer systems have attempt to position a better whole of life, because yes, this vacuum pump station might be $2 million, but when it's servicing 1,500 properties or something like that, then the cost per connection is much lower. However, again, the objective with this is to look past maybe that initial proposal and consider those proposals when it comes down to the cost to install different components within the systems. Again, if we're in flat, low-lying areas and we're open cut trenching to install those vacuum sewer systems, making sure that construction rates are appropriate for any dewatering that might be needed and those sorts of things. But again, it's those flat and particularly large projects to help defer the high cost of the vacuum pump station.
Okay, and I know we're running out of time quickly here, but can grinder pump stations be located outside of private property, and what are the benefits?
Yeah, grinder pump stations can be located out of private property, and it's done, periodically. There are some complexities that do arise when we site a grinder pump station outside of that property. Everything is can be overcome. It's where is it located? What sort of surface is over top of it? Is it an area that pedestrian could walk? Is it an area that cars might be? There's some nuances like that. There's also, because the unit does require electricity, where is the source of that electricity? When a unit is located on private property, it's a little bit easier because we're going to get power from that individual property. When it's on public property, then we have to consider, okay, well, where are we going to get this power from it? Those are the easy things I'd say for this audience. The thing to keep in mind too is the amount of gravity drainage. We are trying to reduce the amount of gravity drainage, and that private gravity drainage, right? That pipe that connects the house to the grinder pump station. The further away from the house or the source of wastewater generation that grinder pump station is, the longer that gravity is. And again, it's been demonstrated that that's where a significant amount of infiltration is coming from. And that's where it's most challenging for a city council, utility, whomever, to do anything about it, because that piece of pipe is the homeowner's responsibility. I don't care what ordinance you have and things like that. That's where all that is coming from. So if anything else, I'd say there's some huge inflow and infiltration benefits that will benefit the collection system, any transfer piping, the treatment plant, just the costs in general of operating that entire system if we can minimize that private drainage. So really long-winded answer to say yes, but again, there's some realities or some trade-offs or some risks that must be mitigated.
Okay, thanks for that. All right, last question.
Okay.
Do earthquake zones present high risks?
So it's funny. So pressure sewer systems have kind of demonstrated their ability to be resilient in seismically active areas. A case that's kind of near and dear to my heart, some deployment of pressure sewers that occurred in Christchurch, New Zealand. Almost 10 years ago now. And for a variety of reasons, Christchurch, in this specific example, a flat, low-lying area with high groundwater, might be a jump ball between pressure and vacuum sewer systems. Though when we look at the risk of future ground movements from future seismic activity, even that vacuum sewer system, when those lifts need to be laid on a particular grade, future ground movements can upset a pretty tight tolerance on that slope. So for that reason, pressure sewer systems have been successfully utilized. And again, not only to overcome those construction challenges, but from a resiliency standpoint, a electrofusion welded high density polyethylene pipe network has kind of demonstrated it'll flex and move along with the ground, and it won't fracture. We won't lose grade because we didn't need grade to begin with. So there's a lot of great benefits when it comes to putting pressure sewer systems in an earthquake or a seismically active area.
Okay, well, everyone, we've gone about 5 minutes over. We thank you for your time and your questions. We're sorry that we couldn't get to all of them. But as a reminder, we'll be emailing out a PDF of Derek's presentation, as well as your certificate of attendance and answers to your unanswered questions within about 48 hours. So on behalf of all of us at E1, we thank you for joining today's session and look forward to seeing you soon. Be well.